Let's start thinking about modeling a binary or two-class response through a motivating example. In an epidemiological study, investigators were interested in identifying the relationship between different risk factors, such as age and presence of coronary heart disease, or CHD. CHD is a binary response. A binary or dichotomous response takes on only one of two possible values, such as disease status, case or control, or response to therapy, responded versus failed to respond. Dichotomous responses are conventionally coded as 0 and 1. It is not useful to fit a linear regression model to a dichotomous response since the response probabilities are confined to a 0-1 scale, whereas regression models could predict off-scale values that are either below 0 or above 1. Instead, a model should be fit on a scale that preserves the range of the response probabilities. Logistic regression is used to model the relationship between a dichotomous outcome variable and a set of predictor variables. To consider how we might model a dichotomous response, let's reflect back to the binomial distribution, where y is the number of successes out of m trials, for example, the number of heads in 10 flips of a coin. Y has a probability function given by this expression, where pi is the probability of success. The expected value and variance are given here. For our dataset, consider that each person is a trial. Let I index each person and let CHD be a success and no CHD be a failure. Then CHD sub I is a binomial random variable and the possible number of successes are 0 or 1 for any individual. So the probability that CHD equals A is given by this expression. Substituting m equals 1 for subject I, the first term goes away, so we are left with this bottom expression. When A equals 0, we get that the probability of CHD equaling 0 is simply 1 minus pi. Alternatively, when A equals 1, we get the probability of CHD equals 1 is equal to pi. As in linear regression, we still want to model the mean CHD outcome. However, in linear regression, there is no restriction on the range of y. That is, y can take on any value from negative infinity to positive infinity. However, the expected value of CHD should be between 0 and 1 because we are modeling the probability of CHD. Linear regression also violates the homoscedasticity assumption when y can only take on one of two values. So a linear regression model does not make sense when modeling a binary response. Traditionally, logistic regression assumes that the observations are a random sample from a population where the model is expressed by this equation, or equivalently as this, where y sub I represents the dichotomous dependent or outcome variable, pi of x sub I represents the conditional probability of experiencing the event given the independent predictor variables x sub I, and epsilon sub I represents the binomial random error term. More formally, the conditional probability pi of x sub I is a function of the independent variable. This, in fact, is the logistic function. In this model, the coefficients can range from negative infinity to positive infinity. Because when you exponentiate, you always get a positive value, the results from this function will always fall between 0 and 1, which is a requirement for probabilities, that they fall between 0 and 1. We do have assumptions for our logistic regression model. First, y is binomial. The expected value of y given x is the logistic function, which implies that the logit is a linear function of x. The logit is the link function for our logistic regression model, as the logit links our model to the linear function of x. The values of y are independent. That means that we have independent observations, or the same subject was not measured several times, or we do not have measurements from twins or family members. So the assumptions are distribution, linearity, and independence. To understand the mechanics regarding how a logistic regression model is fit, remember, for linear regression, we estimate the coefficients by finding the values that minimize the sum of squared errors. However, for logistic regression, we use maximum likelihood, so the coefficients beta naught, and beta 1 are those that maximize the probability of observing the data. We need to write down the probability of observing y given x. A convenient way to express the contribution to the likelihood function for observation I is given by this expression, where if y sub I equals 0, the second part of the equation is observed, while if y sub I equals 1, the first part of the equation is observed. This should look familiar as we saw this expression on a previous slide. We have n observations, so the likelihood needs to include all n subjects. Since the observations are assumed to be independent, the likelihood function is simply the product of the n independent terms given in this equation. Mathematically, it is easier to maximize the log likelihood because the product then becomes a summation, which is then given by this equation. We can differentiate the log likelihood with respect to beta naught and beta 1 and set the equations equal to 0. However, it is difficult to solve these equations because pi of x sub I is not a linear function, but an exponential function, so these equations are nonlinear. Therefore, we use an iterative procedure for solving for our coefficients that maximize the log likelihood, which we call our estimating equations or score equations. Let's go back to our motivating data set. The log odds of coronary heart disease given age is given by this equation. The base R function for fitting logistic regression models is GLM, which is used to fit generalized linear models. Our response, CHD, is modeled by age, where our data frame is heart. To let R know we want to fit a logistic regression model, we need to specify that family equals binomial. The summary function provides different information from the fitted logistic regression model, including the coefficient estimates, the standard errors, the Wald test, which is the coefficient estimate divided by its standard error, and associated p-value. We may be interested in interpreting the parameter estimates. Beta naught is the log odds that y equals 1 when x equals 0. For beta 1, it is the increase in the log odds for a 1-unit increase in x. Let's suppose we have a subject for whom x has a covariate value of a. Suppose we increase x by 1 unit. Now x equals a plus 1. So this is now our logit. Taking the difference between these two, we get beta 1. That is why we say that beta 1 is the log odds increase for a 1-unit increase in x. Beta 1 can also be interpreted as the log odds ratio that y equals 1 corresponding to a 1-unit change in x. Recall that the log of c over d equals log of c minus the log of d, so we can write our expression in this format. Both the numerator and the denominator are both odds, so you have an odds ratio in the interior, so we have a log odds ratio. So exponentiating, we get the odds ratio. The following model was estimated to describe the relationship between CHD and age. Now we want to interpret the effect of age. In this case, the log odds of CHD increases by 0.064 per year increase in age. Personally, I don't care much for this interpretation because I don't think on a log scale. Another interpretation of beta 1 can be in terms of the odds. We know that exponentiating beta 1 gives us the odds ratio. In our example, the odds ratio is 1.07. In other words, the odds of having CHD are 107% times of that of someone 1 year younger. More frequently, we would say the odds of CHD are increased by 7% for a 1-year increase in age. We may want to predict the probability of CHD at a specific value of x. Given our fitted model, we can plug our coefficient estimates to estimate the odds as well as the probability using these equations. Given the estimated model for the log odds of CHD, suppose we want to estimate the odds and probability of CHD for someone who is 65 years old. We substitute 65 into our linear equation and exponentiate to get the odds. Then plugging into the logistic formula, we get the probability of CHD for a 65-year-old. Rather than including only a single predictor, we may want to include multiple predictors in our model. In that case, the scalar x is replaced by the vector x for each subject. All components in the model represent the same quantities, except we now have p predictors, so there are p plus 1 coefficients, a coefficient for each predictor plus the intercept. Again, the logit link transforms the probabilities to the linear scale. We still form the likelihood and maximize the log likelihood to estimate the model coefficients. We still use the base GLMR function for fitting a multivariable logistic regression model, where family equals binomial, to ensure a logistic regression model is fit. Here, CHD is modeled by all other variables in the heart data frame. So this shorthand notation is used. Tilde period simply represents is modeled by all other variables. The summary function provides the coefficient estimates, their standard errors, wald test, and associated p-values. We interpret these coefficients as we did in the simple logistic regression model, although we add adjusting for the other covariates, or controlling for the other covariates, or with the other covariates held constant in our interpretation. Again, you should clearly elaborate on which covariates were included in the model. As in linear regression, we may be interested in testing whether beta sub j equals 0 versus it does not equal 0 in our logistic regression model. In other words, we may want to test whether x sub j is significantly associated with our binary response y, controlling for all other variables. We can compare the predictive ability of x by including it in the model, and then also assess the model when not including x in the model. The saturated model is the best possible model achievable, as it is a saturated model defined as one where the number of parameters is equal to the number of distinct covariate patterns. Therefore, a saturated model fits the data perfectly because it has as many estimated parameters as there are values to be fitted in the model. The likelihood of a saturated model is 1, so the log likelihood of a saturated model is 0. For each model, we compute the deviance, which is minus 2 times the log likelihood ratio comparing the likelihood of the model versus the likelihood of the saturated model. As mentioned, the likelihood of the saturated model is 1, so the larger the numerator, the smaller the deviance. The smaller the deviance indicates a better model fit. The likelihood ratio test is then the difference in deviance between the two models. We can re-express this difference by removing the negative sign and exchanging the order. The test statistic follows a chi-square distribution with the number of degrees of freedom equal to the number of parameters different between the two models. When testing one coefficient, the degrees of freedom is 1. We reject the null hypothesis that beta is equal to 0 if the test statistic is greater than or equal to the chi-square distribution with 1 degree of freedom at the 1 minus alpha level. Otherwise, we fail to reject the null hypothesis. Suppose we have a predictor with k categories. We can create a predictor with k categories represented by k-1 dummy variables. The k categories must be mutually exclusive and exhaustive. That is, subjects must belong to one and only one category. The likelihood ratio test can then be used in a similar way as how we use the partial F test in multiple linear regression. That is, to test whether the group of predictors is collectively associated with a binary response, the null hypothesis is that all betas are equal to 0, and the alternative hypothesis is that at least one of the betas does not equal 0. The full model includes the set of covariates of interest. The reduced model is the same as the full model, but with the covariates of interest removed from that model fit. We then perform the likelihood ratio test. Because k-1 dummy variables are included in the model, the test statistic follows a chi-square distribution with k-1 degrees of freedom. Generally, the likelihood ratio and the wald tests examine the same null hypothesis, but use different statistics and different reference distributions. Note, though, that a wald test cannot be used to test a group of variables. Nevertheless, these two tests are asymptotically equivalent. That is, they yield virtually the same p-values when the sample size is large. When the sample size is small to moderate, the likelihood ratio test has better properties. The wald test is also less powerful. Therefore, the likelihood ratio test is typically preferred. As an example, we had previously fit a multivariable logistic regression model that included 9 predictors. Perhaps we don't need to measure 9 features on every subject. That is, if the predictive performance is as good when using 6 versus 9 variables, we can save some effort on collecting extraneous data. Suppose we want to test the null hypothesis that these 3 betas are equal to 0 against the alternative that at least 1 does not equal 0. We fit the reduced model and then form the likelihood ratio test statistic and then extract the p-value from the chi-square distribution, which, because we've removed 3 coefficients, has 3 degrees of freedom. In this case, the p-value is much larger than our type 1 error of 0.05, so we fail to reject the null hypothesis. That is, we can exclude those 3 predictors from our model because their coefficients are not significantly different from 0. One purpose in fitting a logistic regression model is to predict the outcome, including for future patients. We can use the predict function in R and request that the type of prediction we want is response. In that case, R outputs predictions in the form of a probability. Alternatively, the fitted function also outputs predictions in the form of a probability. You can see the distribution of the predictions from a CHD model. Note that they all lie between 0 and 1. Rather than examining probabilities, which range from 0 to 1, we often want to make a binary decision using the predicted probabilities, such as predicting the binary response of whether or not the patient will develop CHD. To make a binary decision, we need to choose a threshold above which we will say the person is likely to develop CHD. Of course, we could use 0.5 as a threshold, such that if the estimated probability is greater than 0.5, we would predict the person will develop CHD, while if the estimated probability is less than or equal to 0.5, we predict the person will not develop CHD. 2 measures that are frequently evaluated for such binary decisions are sensitivity and specificity. Sensitivity is the proportion of subjects with CHD that have a predicted probability exceeding our threshold. Specificity is the proportion of subjects without CHD that have a predicted probability less than or equal to our threshold. This 2x2 table represents subjects whose true disease status is in columns, while rows represent predictions from the model. That is, A is the number of subjects who have CHD who were predicted to have CHD. B is the number of subjects who do not have CHD but were predicted to have CHD. C is the number of subjects who have CHD but were predicted not to have CHD. And D is the number of subjects without CHD who were predicted to not have CHD. Therefore, we want the numbers A and D to be large because they represent accurate predictions. Again, sensitivity is the proportion of subjects with CHD that have a predicted probability exceeding our threshold, given by this equation. And specificity is the proportion of subjects without CHD that have a predicted probability less than or equal to our threshold, given by this equation. Note that sensitivity and specificity are dependent on the threshold, and therefore our interpretation of model performance likely changes depending on the threshold chosen. A more comprehensive approach would be to examine sensitivity and specificity for all possible thresholds. In fact, a receiver operating characteristic curve, called ROC curve, is a graph that plots the sensitivity versus 1 minus specificity, allowing us to visualize both measures for any threshold. The closer the ROC curve is to a diagonal line, the worse the model performance, as the diagonal line represents performance that would be achieved by randomly assigning a binary class using a coin flip. The closer the ROC curve is to the upper left-hand corner, the better the model performance. The R package, PROC, includes a function, ROC, that can be used to plot the ROC curve and calculates the area under the curve. Again, this diagonal line represents the performance that would be achieved by randomly assigning the binary class using a coin flip, and the area under this curve is 0.5. The area under the ROC curve, called AUC, can take on a maximum value of 1, which would indicate a perfect predictor for any threshold. AUC values closer to 1 indicate better fit than AUC values closer to 0.5. The larger the area under the curve, the better the fit. When evaluating AUC results, these rules of thumb can be used for interpreting the AUC. If the AUC is equal to 0.5, the model does not discriminate. The model is no different from flipping a coin. Note, if the AUC is less than 0.5, there is likely some error in your modeling method. If your AUC is in the 0.5 to 0.7 range, you have poor discrimination. If your AUC is in the 0.7 to 0.8 range, you have acceptable discrimination, while the 0.8 to 0.9 range indicates excellent discrimination. And greater than or equal to 0.9 is outstanding discrimination. In practice, if you develop a new model to predict an outcome, compare your model's AUC to the best available existing method's AUC. Selecting a threshold depends on the goal of your study. If you want to rule in a diagnosis, you want the threshold that maximizes specificity because you need the number of false positives to be low. If you want to rule out a diagnosis, you want the threshold that maximizes sensitivity because you need the number of false negatives to be low. The thresholds associated with all the values of sensitivity and specificity can be extracted using the coords function in the PROC package. If you do not have a preference between sensitivity and specificity, you can maximize them both at the same time, which is called using Youden's index, and you additionally specify x equals best in the coords function. For our CHD model, the optimal threshold using Youden's index is 0.32. Penalized logistic regression models can also be used for variable selection and shrinkage, where the log likelihood is modified by subtracting the penalty term. Again, the parameter lambda controls the amount of shrinkage. To fit a ridge penalized logistic regression model, we maximize this equation. To fit a LASSO logistic regression model, we maximize this equation. To fit an elastic net logistic regression model, we maximize this equation, where here alpha controls the relative proportion of the penalty applied to the ridge versus the LASSO. The R package GLMNet can also be used for fitting penalized logistic regression models. When fitting a penalized logistic regression model, the family parameter is set equal to binomial, and our response takes on values of 0 and 1. To fit a ridge penalized logistic regression model, set alpha equal to 0. To fit a LASSO penalized logistic regression model, set alpha equal to 1. To fit an elastic net penalized logistic regression model, set alpha to some value between 0 and 1. Each model is fit for a sequence of penalty parameter values lambda, and then we need to identify which lambda to use for establishing our final model.